Thank you all for joining us today. Really excited to see our best turnout yet at a meetup. We have maxed out this room for sure. So thanks for joining us. To give you a little bit of background on this meetup, on if you're confused as to how you showed up here, this is the Bay Area Research in Natural Language Processing and Machine Learning meetup. And there are a lot of meetups out there on machine learning and natural language processing, but the real focus of this one is on research. So we're really interested in novel approaches, things that haven't been done before, research that's been published recently. We want to kind of understand where people are pushing the limits of the state of the art. A little bit of background on Maya. If you haven't noticed, on the back wall plastered is the name of the company sponsoring this event, Maya. So Maya Systems is a company that brings deep learning and NLP expertise together in the end-to-end recruiting process. And we have a digital assistant named Maya, just like the name of the company, who interacts with candidates throughout that process. Just a quick note, we are hiring if you're interested, and Lauren, who's at the back, who's our head of recruiting, would be happy to talk to you. As I do in every meetup, I wanted to make a quick note, and it's the only time I'm going to ask that you take out your phones really quickly and open your calendar app and make note of our next meetup. We're really excited. We have a postdoc from the computer science department and NLP group at Stanford, who just last month released a new data set called COCA. And he's going to be talking about that data set next month. So if you're interested in that topic, please join us. And so make sure you save the date. Next, on all of our meetup pages, you'll see that we have a Google form for submissions for external speakers, so speakers that aren't in Maya. Like, for example, Siva Reddy, who is going to be talking in October, is an external speaker. If you have an idea, it doesn't have to be completely fleshed out, doesn't have to be published, but if it is something that's pushing the boundaries of AI, we're really interested in considering that. So please follow the Google form that you'll find on all of our meetup pages to submit that idea. Next small detail, there is a key on the back wall for the restrooms if you need to use that during the talk at any time. So now I'm going to go ahead and introduce our speaker today. So just a little background on Amir. So Amir Kargar is a machine learning engineer at Maya Systems. He received his bachelor's degree in electrical engineering from Shiraz University and his master's degree in computer engineering from University of Denver. He first started working on conversational agents when he was developing an interactive social robotic platform called eBear as his master's thesis. And previous to Maya, he has worked on a conversational agent for the elderly people with dementia, as well as a medical conversational agent. And here at Maya Systems, his focus is on natural language inference and paraphrase detection. And so a little bit of details as to what he'll be talking about. So his talk is, as you probably figured out from the title, is going to focus on machine learning approaches to natural language inference, which, as we all know, is a subtask of natural language understanding. And NLI typically involves two natural language inputs, a hypothesis and a premise, in the form of text. And the task is to determine the relationship between these two natural language sentences, whether the hypothesis is an entailment, contradiction, or neutral in relation to the premise statement. Most of the state-of-the-art literature in natural language inference shares the same paradigm of encoding, attention, inference, and classification, but Amir's going to go over two well-known models, RNNs and transformers, and how each of their steps are done in detail and compare the accuracy of these models on SNLI. So without further ado, please welcome Amir Kargar.
Thank you everyone for joining us today. As Zach did the introduction, my name is Amir Kargar and I'm a machine learning engineer here at Maya Systems. Today I'm going to talk about natural language inference, and basically we are going to compare two well-known deep learning model in the case of natural language inference, or NLI. So here's the outline of my talk. First, I'm going to define what is natural language inference and give you a few examples. Then I'm going to talk about the most well-known corpora in the case of NLI. And after that, I will talk about what is the goal of my talk. There is a code that comes with this talk. I'm going to give you the link at the end of this talk, and you can go on that repo on GitHub and check it out, run it for yourself, and play with parameters. So I'm going to talk about the goal, and then there is a architecture that we chose to run those two well-known deep models within that. And then I will talk about each module of that architecture in details. I will try to cover everything from scratch. So in advance, I'm sorry if some of the things I'm going to talk about might be, you might be already familiar with that. And then at the end, I'm going to talk about, I'm going to give a brief, I'm going to talk about one of the experiments that I did on this, with this code. So what is natural language inference? The main idea of natural language inference is to be able to determine if a natural language hypothesis is, can be inferred from a natural language premise. I mean, as I said, these are natural language, so they will be both text. Usually they are denoted with H and P. This is also called like recognizing textual entailment, RTE. I mean, first when it was introduced, it was RTE, but right now we mostly know it with NLI. And it was first introduced in 2004 as a binary classification. And so it was a binary classification task, whether a hypothesis is entailed or not entailed, given the premise. But later on, they changed the task into a 3-class classification task. We will have 3 classes. One of them is entailment, contradiction, and neutral. In the case of entailment, given the hypothesis, given the premise, we want to see if the hypothesis is entailed or no. In the case of contradiction, given the premise, we want to see if the negation of that hypothesis is entailed or no. And in the case of neutral, no entailment. So these are the 3 classes of NLI. Why we are interested in NLI in the first place? So NLI is one of the main components of a full natural language understanding system. So if we want to have a full natural language understanding system, we want to be able to understand all the implications in a sentence. So if we cannot understand that, then what's the point of a full NLU system? So that's one main reason why we are interested in NLI is because of NLU. And there are a few cases that we can already use it. One of them is question answering systems. So given a question, and let's say we come up with a few answers from the resources that we have, web or whatever we are using. So we want to see what is the relationship between that question and those answers. So NLI becomes handy in this case. The other case is automatic summarization. In these summarization techniques, we want to make sure that if we have a sentence in the text, we don't want to have any redundant sentence in that text that is basically have the same meaning as this text. So we want to make sure there is no redundancy. So that's the other case we can use NLI. And then at the end is the other use case is semantic search. So the user searches for something. Usually we look for keywords, but it would be better to not only look for keywords, but also look in the meaning and try to find something which meaning-wise is the same as what the user searched for. So it would make it more efficient. So that's why we are interested in NLI. And actually there are many more use cases. These are just a few. So the task that we are looking at is we have 2 inputs. One of them is the premise. The other one is the hypothesis. And it's a 3-class classification task: entailment, contradiction, and neutral, as you can see. So that's the main task. Now I defined what is NLI and the 3 classes. Now let's look at a few examples. The first column is premise, the third one is hypothesis, and the middle one is the relationship between them. So in the first row, a man inspects the uniform of a figure in some East Asian country. This and the man is sleeping. So the negation of the man is sleeping is entailed in the premise, as you can see, because the man is doing something, but here it says the man is sleeping. And in the case of neutral, an older and younger man smiling versus 2 men are smiling and laughing at the cats playing on the floor. So you cannot really find anything between them. There are some things in common, but meaning-wise, they're neutral. I know that some might argue right now that there are things in common between these 2, but I guess we have to rely on the what the annotators do in this case. And in the case of entailment, the last row, a soccer game with multiple males playing. Some men are playing a sport. This is entail within that. So that's the entailment case. These are a few examples. Now let's go to look at, some of the well-known corpora in NLI that usually researchers use in order to report their accuracies and run their models on. The first one, and probably most of you know about it, this is called Stanford Natural Language Inference Corpus, or SNLI. This is relatively old. It has 5,700 sentence pairs. Premises are sentences from Flickr, and the hypotheses are manually annotated using crowdsourcing. Here are a few examples. In a bit, I will show you like leaderboard on for all the data sets that I'm going to talk about to see who is having the best accuracy right now. So this is the first one. The second one is called multi-genre NLI or multi-NLI. This one has less number of sentences, 433,000 sentence pairs. But there are two big differences between this one and the last one. First of all, there are three differences. One of them, this is a newer version by the same group, but this is a newer data set. And the other difference is that this has 10 distinct classes or genres. And as you can see in these examples, each of the examples, they have an extra tag genre. So you can do the classification within genre or cross genres. And the other difference is that it has both written and spoken text. As you can see, we have telephone speech and like letters, so both written and spoken text. The other one, which probably I wasn't aware of it until a while ago, so not that well now, Sitel corpus. This has one big difference. There's one big difference between this one and the two previous ones that I talked about, and the difference is that this was not crowdsourced. So looking at this example, there is a question, and it's a multiple choice science question, and the number, C is the right answer. So adding C with the question gives us the hypothesis, as you can see here, and then the premise sentences are they gathered it from like doing web searches and finding from web. So these are like two example premise sentences which they got from web. So they did not do crowdsourcing in this case. So these were the three main corpora that usually people use. Now, what is the goal of our talk today? So there are three main deep learning models out there for sequential data. One of them is recurrent neural networks. The other one is convolutional neural networks, and a new model called the transformer model, which was introduced in 2017. The goal of this talk is to compare recurrent neural networks with the transformer model. I did not do compare the CNNs, but that could be another project by itself. So I'm going to compare RNNs with CNNs. RNNs the nature of RNNs are sequential, so that's usually the go-to models for the cases that we are dealing with sequential data. But the transformer model is not sequential in nature by itself, but they claim that it's all you need. That's the name of the paper. Attention is all you need. So we want to compare these two models. And we have two ways to go about it. One of them is to look at, let's say the data set that I just talked about and see in their leaderboard who's doing a better job. But we thought it would be more fair to design a main architecture and then use these two models within that architecture and see which one is doing a better job. So because with state-of-the-art models, usually people use all different kinds of, usually they add all different kinds of like modules or do different kinds of tricks like transformer learning, or there are many things that you can do to increase the accuracy. And of course, I mean, I'm not against that, but I'm just saying that if you want to have a more kind of a fair comparison, it would be good to compare them within single architecture. So that's what we want to do in this talk. So looking at the state of the art for different corpora that we talked about, SNLI, this column is RNN, recurrent neural network. This is transformer, and this is attention mechanism that I will talk about later in the slides. And as you can see, for SNLI, the number one is RNN, which is doing a better job than transformer. But as you can see, the differences are not that high. So I can say they're doing the same job. I mean, I can't say that, but they're close to each other. But the rest, as you can see, is only RNN and attention. And we have down here, we have a human performance, which is kind of interesting. So what it means is that they asked 5 people to sit down and look at SNLI data set, the test part, and ask them to label the NLI problem for SNLI data set. So the average accuracy was 87.7. So we can say that the machine learning beat human here, but one might argue that no, I mean, what if, I don't know, I can find someone who has a better IQ than those 5. So, but relatively saying, we can say that machine learning is doing a good job in compared to human.
How do you mind ask questions?
Would you mind write it down and then ask at the end? Sorry about that. So that was SNLI and multi-NLI. The other thing about multi-NLI and Sitel that I forgot to say is that these are newer models, so not that many people have tried to use these. Sorry, these are new data sets, and not that many people have tried to train their models on these data sets, so there will be less data on it. As you can see, for example, for multi-NLI, transformer is the number one with a huge difference in compared to this ones. And as you can see, they're all 2018 papers, so they are all new, but transformer is beating the rest by at least 10%. And these 2 ones are RNNs, one with attention, one without attention. For Sitel, I only have 2 data points. One of them is the transformer, which is doing a relatively good job in compared to the one before that, at least like 5%, 6%. So as we saw in SNLI, RNN and transformer, they are kind of the same, but for the 2 other ones, transformer is doing a better job. Now let's see what it happens in our case. So now I'm going to talk about the architecture that we chose. I mean, this is a common architecture, as you can see here. It's not something that we designed, we just chose it. I'm going to talk about all these modules in the later slide, but to give you some general ideas on what each module does. As I said before, some of them would be, I mean, some people probably would be already familiar with some modules, but I'm going to briefly go over all of them in case someone doesn't know. So we have 2 inputs. One of them is the hypothesis. The other one is premise. These are text inputs. We feed them into our embedding module to get the kind of a mathematical representation of that text. And in the case of transformer, because it's not a sequential model, we need to add some positional information. That's why we use this module. And then the encoding part, which is the focus of this talk, is where RNN or transformer is applied. And then at the end, we want to aggregate, get all the results from these 2 outputs, and then apply a softmax on top to get the classification results. So that's basically what we are doing in this architecture. Now let's take a closer look at each of these modules. The first one, as I said, is embedding. What is the idea behind embedding? We have a sentence as input. A sentence is a bunch of words, and what we want to have is a mathematical representation of those words so that we can feed them into our deep models. So here, these are like different words in that sentence, and each of these x's are, as you can see, these are vector representation of that, for example, word n, vector representation is xn. So that's what we want to do. But how we do it? One thing I need to say right now is that the rest of the things that I'm going to talk about is not specific to NLI. It's probably most people use it across different NLP problems, but most of them are like good practices for like different NLP problems. So they're not specific to NLI. Let's say we have a word as input and we want to get a vector representation as output. We can look at the word from two different perspectives. One is from a word level perspective, the other one is from a character level perspective. So looking at it from a word level perspective, there are a few well-known methods to convert a word into a vector representation, word2vec, glove, or fasttext. I'm not going to go into details of them, but to quickly go over them, what they do basically, they are a kind of a lookup table. Let's say we have already trained them. They're a kind of a lookup table. They take the word as input and they give us the vector representation as output. But the way they work is that if two words are, again, most of them know it, if two words are close to each other in terms of their meaning, then their vector representations are close to each other in terms of distance. So that's the main idea behind word representations here. And now let's look at it from a character level point of view. Each word has a bunch of characters. And what we can do, we can feed them into a recurrent neural network or a convolutional neural network to give us a vector representation of that word. And then at the end, usually how they do it is they concat the results to get the final vector representation. The main advantage of using both character level and word level is that, so I talked about word level and what it gives us, but what about character level? It gives us two advantages. One of them is that in case we have a misspelled word, because we are dealing with characters, not words, because in case of word level, let's say the word is misspelled, we cannot find it in the lookup table. So either it gives us a random vector, or it gives us a predefined vector, or sometimes it gives us like the average of the words next to it, something like that. But with character level, let's say one of the characters is wrong, still the rest are correct. So the chances of having a vector which makes more sense is higher. So it's really strong against misspelling. The other advantage of character level is that if we have a word which is not in our vocabulary, still the character level can like give us a vector representation. Why? Because like let's say we have 28 or 30, 40 characters. We already define all of them in advance. We know it's a limited number of characters, and each word is created with a bunch of vectors, with a bunch of characters. So there wouldn't be any case. It doesn't make sense to have a word not in the vocabulary. There's always something because we have already defined all the characters for our CNN or for our RNN. So that's how the embedding is done. Again, if you had any questions at the end, you can ask, sorry. Positional encoding. The main idea with positional encoding is to be able to kind of add some positional informations to each token. This is useful for the cases where there is no recurrence or convolution. So as I said, RNNs, nature are sequential, but the transformer model is not sequential. So we have to somehow ingest positional information. There are two types. One of them is learned, the other one is fixed. But they have showed that usually the learn and the fixed, they don't differ that much, and it's easier to use the fixed one. The way we do it is that, this is just one option of doing it. What you see here, there are many ways, but that's how they did it in the annotation is all unit paper. And they claim that by using it, because it's basically a bunch of sinusoidal waves, which have different frequency and different offset. So, and they claim, the hypothesis is that by using sinusoidal wave, it would help with extrapolation. That's the main idea of why they want to use sinusoidal wave as opposed to anything else. So we have two inputs here. One of them is the position. The other one, I, is the dimension number. So position is the position of the word. I is the, let's say we have 100 dimensional word embedding. So I would be from 0 to 99. And so, and the difference between sinus and cosine, as you all know, is like 90-degree difference. So basically, they are the same. This is an example. This axis is the position. This 0 here means for token number 0, what we do, we add whatever information is across here. So this is just an example for dimension 4, 5, 8, 6, and 7. So in case of 100 dimensional, we will have 100 different sinusoidal waves here with different frequencies and with different offsets. And for each position, we add all the information to the corresponding dimension in the vector representation. So in this way, we are somehow ingesting positional information. Now let's go to the kind of the most important part, which is encoding. What is the idea behind encoding? We have a symbol representation as input, and we want to get a continuous representation or context as output. What does it mean? The symbol representation is like what we got out of that embedding module. So it's a vector representation, and it knows what that token is, what that word is, but it has no idea. Like, let's say, look at x1. It has no idea what is x2. It has no idea what is x3. Or let's say we have sentence x, and there is another sentence y here, that we want to compare them to each other. So x1 doesn't know what are the other tokens in the other sentence. So the main idea of encoding is to let each of them know what's going on in their sentence and in the other sentence that they are being compared to. So here, Z1 not only knows what is X1, but also knows what are these other tokens and the other sentence. So that's the main idea of encoding. The first encoder that we're going to talk about are recurrent neural networks. So RNNs, they have been around for a while. And as I said, their nature is sequential, and they take into account the order of the words. So that's what I mean by sequential. They were built for sequential data and like machine translation models, many text-related, NLP-related models. RNN still is doing a great job. And I know most of you know about it, but I'm just going to quickly go over how this works. This here is one unit of RNN. We can have other units like on top of each other to make it like a multi-layer RNN. But the simplest case, we have an input X, we have an output O, and a hidden state S. So let's say we have a sentence. We grab the first token, we feed it into this unit as X. We get an output. At the same time, this hidden state gets updated. And then we do it for the next token, and then we do it for the token after. So we do it until the whole sentence is fed into this unit. If I unfold it, basically whatever I just told you, what happens is that, let's say the output at time step t, it depends on the input of time step t, and the hidden state of the previous time step, st minus 1. So output t depends on st minus 1. So this shows that sequential nature that I just said. To kind of give you how this works from a mathematical perspective. First of all, I'm talking about RNNs in general. There are different types of RNNs like LSTMs and GRUs and even more. But this is how in general they work. We have a bunch of outputs, bunch of inputs, and this H here is that hidden state that I talked about in the previous slide. And the way it works, H of t is depends on x at time step t multiplied by a parameter, and the hidden state at time t minus 1 multiplied by another parameter, w, and then we feed all of them into a sigmoid to get the hidden state of this specific layer. And then in order to get the output, we multiply that hidden state by another parameter, and then just a softmax on top of that to get the output. So that's basically how RNNs work. In the case of LSTM or GRU, the the structure inside here is different. The way that they update the hidden state is different, but we are not going through details of that. So as I said, RNNs are sequential. That's the plus point of RNN, but at the same time, it's a negative point about RNN. Why? Because when the nature of something is sequential, so then means that we cannot make the system in kind of, how to say that, because it's sequential, we have to feed in every token and then the token after that and then the token after that. We cannot feed in all the tokens at the same time because each token depends on the information from the token before that. So that prevents parallelization. So that's one problem with the recurrent neural networks. The other problem is that they have a kind of a less structured memory. What I forgot to say in this slide is that this H, the hidden state, sometimes is called the memory. H is a fixed length vector, and it is supposed to capture the context of the whole text. So let's say you have a text like 20, 30 token long, and this one fixed length vector is supposed to capture the meaning of all of that. So it's kind of less, that's what we mean by less structure. So it's only one vector, fixed length vector, which is supposed to capture everything. And what that causes is that it's only able to capture short range linguistic structures. So these are the two main problems with RNNs. Now the other encoder that we're going to talk about, the transformer. This was introduced in 2017 by researchers from Google. The nature of the transformer model is not sequential. This is transformer model. I'm going to go through details of each of these modules and then come back to this slide to talk about how this works. But so this is, first of all, this is not a sequential model. And then this has a more structured memory. So it's able to handle dependencies in like longer texts. And it's fully based on attention mechanism. Now let's see how this attention mechanism works. We will come back to this slide. Attention. What is the idea behind attention? So let's say we have two pieces of text and we want to compare them. One of the first steps that we want to do is to align these two pieces of text. What does it mean? It means that, like, let's say we have two pieces of text here. One of them is this one, the other one is this one. We want to somehow calculate a similarity measure between each token of this sentence, like Gazprom bill, double Georgia's gas bill. Calculate the similarity measure between, for example, bill and this whole sentence. So there are many ways to go about it. And that's why we have hard attention and soft attentions and a few more, but these are the most used ones. What is a hard attention? Looking at this image, you can see that we have one sentence here, another sentence there. So for example, men here. Men is from this sentence. Let's say we want to compare the similarity. I mean, we want to calculate the similarity score between men and this whole sentence. With hard attention, as the name shows, men hardly attends to each of these tokens. And at the end, probably would see that men is the closest to males in terms of meanings. That's why it's black. Oh, I forgot. So white means no match, black means match in this case. Usually it's the other way around, sorry. So men is the closest to males among these tokens, and that's why we have a match here. Playing, we have this exact token in the other sentence, we can see here. Some probably is the closest to multiple, that's why we have a match here. So as you can see, each token hardly attends to another token in the other sentence. So if we have like, if we want to see what's the similarity score between men and this whole sentence, we see that how close males is to men, and that single score represents the whole thing, which kind of doesn't make sense. Why does it make sense? Because there is something called soft attention. I mean, this is an example here. So these colors are not real, but I just wanted to give an idea. With soft attention, the way it works is that, let's say we have men here. We calculate some, I mean, I will show how we calculate that. but we calculate a similarity measure between men and each of these tokens, and that would be these colors here. And at the end, the token men not only attends to males, but also attends to all these tokens in the other sentence. Now let's see how this works. Hopefully that would give you a better idea. We have two sentences, X and Y. In the case of X1, we take the vector representation of X1, and we have the vector representations of all the tokens in the Y sentence. So what we do, we multiply them, and then we keep doing it for all the X2, X3, X4. So this is what we get. We, as I said, multiply each of these tokens, vector representation by all the vector representations of these tokens. This is what happens from mathematical perspective. This is how they do it in attention all you need paper. The difference is in this denominator, the normalization factor that they have, but basically it's the same thing. And what happens is that we have Q, K, and V, query, key, and value. In this case, in our case, query is the sentence X, and key and value are equal to each other, equal to sentence Y. So what happens is that we are doing a matrix multiplication between our query, our X, and our Y transpose, because we want to multiply them. And then it's like a normalization factor. D means the dimension of whatever we have for our embedding. And we feed that through a softmax, then multiply it by our V, which is again our Y. So what it gives us is this. What is it? This is a kind of a lookup table. This would be our sentence X, this would be our sentence Y. And each of these cells, what they mean, for example, in the case of X2, it means that X2 and Y1, they have this amount of similarity. X2 and Y2, they have this amount of similarity. So with soft attention, each token not only attends to the closest one in the other sentence, but also attends to all the tokens in the other sentence. So going back to this example here, like double here, double is not only close to increase, but also close to twofold. And what if there's another token somewhere in this sentence which is also close to double? So with soft attention, we calculate the similarity between all these tokens, and they would represent how close double is to this whole sentence. That's the main idea with soft attention. So yeah, now going back to the transformer model, we have an input, we have an output. The input is our embedded sentence. The output is our encoded vector. And the way it works is that I'm going to go through details of these modules as well, but to give you some general ideas, we take the input, feed that into a multi-head attention, which is a special kind of attention. And then there is a residual connection. Basically, what residual connection means is that we grab the input, add it to the output of this layer, that's it. And then we do a kind of layer normalization. After that, there is a neural network, simple feedforward network with residual connection, and then another layer normalization, and it gives us the output. But the main thing is that we keep repeating that n times. So we take the output, feed it in as the next input, and keep doing that for n times. And then at the end, we grab the output as the encoded version. Now let's see what is multi-head attention. As the name shows, it's a multi-head attention. So it has different heads. Each of these blocks are considered as a head, and they're identical. And the way it works, we have an n-dimensional vector as input. The way it works is that first we apply a linear layer on this n-dimensional network. What it gives us is a vector with smaller number of dimensions. Here in this case, because we have 4 heads, it would be a vector, an n-fourth dimensional vector. Then we apply the same soft attention that I talked about on that smaller vector, and then we concat the results of all these heads. Usually here there is another linear layer too, and then at the end we get to a vector which has the same dimensionality as the input. So that's basically how it works. I will show the mathematical formulations in the next slide. But what is the main idea behind multi-head attention? The main idea is that because we are using different linear layers to decrease the number of dimensions, the hypothesis is that in this way, each of these heads will be able to kind of attend to different parts of that vector, input vector. By different parts, I mean looking at it from a different perspective. Why? Because we have different linear layers here, and they are initialized, let's say, randomly. So while training, they hope that each of them attend to different perspective, point of view of this vector. Here, we have Q, K, V, query key value, same as soft attention that I explained. Query is our X in our case, K and V are our Y sentence. So what we do, we multiply them by a weight. This is the linear layer that I showed in the previous slide. So each of them have their own weights, and then we apply the attention on top of that. This would be head 1, like head I, whatever, because we will have multiple heads. And what we do after that, we concat the results of all these heads. As I said, sometimes there is another linear transformation on top of the concatenation. This would gives us the multi-head attention results. So that's how multi-head works. Now let's go to layer normalization. So layer normalization is not something new. We have been using it for a long time, but mostly we used to use it as a pre-processing step, or sometimes on top of our network. But they kind of decided to use it all over the place, not only beginning at the end. And what it causes is that it makes the convergence to be faster, and usually the overall accuracy is higher. Why is that? Because what layer normalization does is that it tries to keep the output of that layer to have a mean around 0 and a variance around unit. And what it does is that, let's say we are not using layer normalization, there might be some outliers in the output of a layer. And during training, the gradient would try to compensate for that one or few outliers. But once you use layer normalization, there won't be any outliers. So it would make it faster, and overall, there will be higher accuracy. At least that's what is, but what the theory is. So in reality, it might be a little bit different. I thought it might be easier to show it by a code, what happens in a layer normalization, in the normalization layer. We have two parameters, A and B, and an epsilon. So we take the input, which is X, and we calculate its mean and its standard deviation. So X minus mean divided by the standard deviation. And there is an epsilon in order to avoid the division by 0. And we multiply the whole thing by one of the parameters and then add the other parameters to it. The reason we are using these parameters is to shift and scale the output. So as I said, usually the mean is 0, the variance is unit. What if the network wants something else? So that's when A2 and B2 helps. This is how normalization is done. Going back to the transformer model. So we talked about multi-head attention, we talked about layer normalization, but there is this position-wise feedforward. This is what happens. Basically, we have two linear transformation. One of them is this one here, and then this max is a ReLU activation function, and then another linear transformation on top of that, and then we get the output. So it's just a simple feedforward neural network. Then we get the output, and now the last module, which is the aggregation module. what happens is that we have the premise and the hypothesis, and once we encode them, we have the encoded premise and encoded hypothesis. So now we want to somehow compare them. So these encoded feature vectors, they already contain many information, all the attentions and everything. Usually a common practice, again, across different NLP tasks is to concat these two vectors, subtract them, and then apply a dot product between them, and concat the results, and fit it into a multi-layer feedforward neural network, and at the end, a softmax on top of that to get the output. But that's how they usually do it. So there might be there is other methods too, like some might use a LSTM on top, a kind of RNN on top of it, and then get the output. So we can concat these, feed into a RNN, and then get the last hidden layer. So there are many ways. This is just one of them. So that's the transformer model. Now I did an experiment on it. Actually, I was doing more experiments on it, but still they are running. So I'm just reporting the results of one of my experiments. The rest, because we open source the source, you can either check it by the end of this week or even train it for yourself to see. This one that I trained. So I'm going to talk about each of the modules and what we did. We got, for the embedding, we used a 100-dimensional glove vector. And then in the case of transformer, the positional encoding that I talked about. And for the encoding module, we have RNN and transformer. And what we do to reduce because we will have sentences with different lengths, for now, we just took the average of those sentences. And then on top, there is a 4-layer feedforward neural network plus ReLU activation and a dropout to get the output. So in the case of transformer, our NX is 4, so we are repeating the whole model 4 times. We have 10 heads, and this is our learning rate. I had to decrease the learning rate to be able to train it using Adam Optimizer and with 50 epochs. In the case of RNN, I only used 1 layer of RNN, so this is the simplest case. Can increase that one. And as I said, there are different types of RNN. I use the LSTM type, and the learning rate is higher than the transformer one. Same optimizer and the same number of epochs. Now let's see what happened. In the case of RNN, after 50 epochs, 74.58%. Transformer, 73.94%. So, I mean, very close to each other, but RNN is a little bit more accurate than transformer. First thing to notice is that this accuracy, even the higher one, is not close to state of the art, and that's because as I showed, I used a very simple architecture. I'm using more architectures, but you can check the repo and see the results. I myself, I'm still waiting for it to see how they compare. Number of parameters, transformer has like another 500,000 parameters more than RNN, but in terms of time, almost the same. The main thing is that I didn't try to parallelize the whole thing, like feeding all the tokens at the same time. So probably if I do that, it will be less than 10 minutes. But the other interesting thing is that these are the diagrams of when I was training it. So this is the train accuracy. As you can see it here, the gray one is for transformer, the green one is the RNN. Usually during training for the train data set, the accuracy of RNN is way higher than transformer. But looking at the test accuracy and even the development set accuracy, you see that with RNN, it usually gets to the top, usually gets to the highest accuracy pretty fast, like within like 2 or 3 epochs, and then it stays there. But with RNN, I mean, one reason is that I had to decrease the learning rate to be able to train it. But as you can see, it took it like, here is it at the end of 50 epoch. So it took a very long time. And I don't know, probably if I had like more number of epochs, it would have even passed the RNN, but up to 50 epochs, it was a little bit less than RNN. So yeah, that's how the experiment was. And you can find the code here. We will add it to the meetup page too. And I will add more results to this once I get the results. I'm kind of excited myself too, because I didn't expect to see a single layer RNN doing a better job than the transformer. And the other thing is that I tried to visualize some attentions, and I have a slide on it, but it doesn't make sense. So the main thing, I mean, the main thing is that they introduced transformer and they train it on a machine translation task, which the dataset is very huge. But in our case, the dataset is not that huge. That might be one reason. Because I tried to play with hyperparameters and get the highest accuracy, but that's all I could get. So this is, first of all, this is the self-attention. So this is a sentence attending to itself. But I really did my best to make sense out of it. I couldn't. So some of you might play with hyperparameters and get a better results, but I couldn't. And as I said, my guess is that because the SNLI data set is not that big enough for transformer, especially because we have multiple layers, and I was not able to train it with a learning rate of 0.001. I had to decrease it. And the other experiment that I'm running currently is that attention is all you need. They also introduce a special kind of optimizer using that one too. And the way that one works is that at the beginning, they increase the learning rate, but after 4,000 steps, they decrease it. So that might help with accuracy and might help with like this too. I'm not sure with, the attention visualization. I'm not sure, but yeah, thank you guys. Any questions? Sure.
Just trying to clarify some of your tables. You have 3 columns. One with RNNs, the other one is.
You mean for the corpora in the corpora section? Yes.
Right. So just trying to understand this table. When you have a circle under RNN and attention, means that you're using RNN and attention together.
Yes.
So that seems to help.
Yes.
As expected. Have you looked at bidirectional scan with that?
So the thing is that I try to use the simplest RNN that I have, which is a single layer, single direction RNN, and that's what I got. So I was planning on like doing this, and then if transformer was way better, try to improve my RNN, add by LSTM, add more layers on top of it. And one thing to notice here is that so the transformer has a special kind of attention, but these attentions are a kind of a vanilla attention, I can call. That's what we have here as the soft attention. So yeah, this is what they are using mostly. So they are not using multi-head attention. The main point of the transformer model was this multi-head attention.
No, what I'm wondering is the transformer is the latest and one of the latest and greatest, and it's quite advanced. But techniques that you're using on RNN, you can push it a bit more. You can do better things and have more layers. So you're kind of comparing RNNs, plain vanilla RNN, with something which is much more advanced. Is that a fair comparison?
Yeah, that's what I did, but that's what the result. I mean, you saw the results. That was the simplest RNN that is out there, right. But the other one.
The cases that RNN lost, it seems to me you could, the difference wasn't that big, then you could make the RNN just as good.
You mean these cases? Because this is like, RNN is like 10% less than the other one. To be honest, I haven't looked at the details of these papers that much. I know that they are using RNN, and for example, in this case, they're using attention, but I'm not sure how they do it. But usually the way they do it is that they apply like RNNs on each input, and then they apply kind of attention on top, and then they do the aggregation. So, I mean, I didn't get your question like fully.
I can talk to you after.
Yeah, because the transformer is a newer model, and that's what I was hoping to get a higher accuracy, but I didn't. I'm still gonna do my best to beat RNN.
I'm guessing that the question is, you're going to compare the transformer model. Why don't you compare with the best that you can get in the RNN world, meaning like a prime direction
Yes.
instead of just a basic RNN? What would be the outcome of that comparison?
So, I mean, that was the trend of my experiment, to start with the like a most basic one. Of course, I mean, probably if I try a BiLSTM and like multiple layers, it would do a way better job than this one. So definitely I'm going to add it. So if you check out the repo, like probably by the end of this week, I will get the results. I wasn't able to finish it by today.
Hundreds of sine waves and cosine waves. The first thing I thought of was Fourier series. Is that
why?
I mean, you're dealing with hundreds of sine and cosine functions. Couldn't you generalize it as some sort of Fourier series?
So the first thing is that this is just one option of doing it, but I don't get why you say Fourier series?
Because it's the sum of sine and cosine waves.
I mean, that's true, but here the main idea is that for each position, we want to have, like for each dimension of each position, we want to have a different value. But if in that case, it wouldn't be like this, using Fourier transformer. But as I said, there are other methods for this. I haven't checked them out.
On your plots, it looks like a transformer can learn more when.
I mean, if I had continued to more than 50 epochs. Yeah, I mean, you're right. That's what I said, because I kind of I didn't have enough time. Like, I mean, it finished like this around noon, so I couldn't do it again. That's why I'm saying, like, if you check it by the end of this week, I might have other results. I don't have the loss diagrams right now, but looking at the loss diagram, it was something like this in case of transformer, I mean, in all cases. So it sounded like that it might go a little bit higher, but not way higher. But you're right, I mean.
Yeah, one of the complaints I've heard about SNLI is that you get a much better accuracy if you just ran it against the null premise. I'm curious what the results would be.
Sorry, can you say that again? What's that?
If you just run it against a null premise, so if all you did is hand it the hypothesis, without even telling you.
That would be 60 something, I think.
Yeah, it actually gets quite good. And I'm curious whether there's any significant difference in the two approaches against that particular simplistic analysis as opposed to this. Again, I really do have time.
So the thing is that when we are trying to train a network, so you initialize all the weights like randomly or something. So saying that, comparing that to a case where you only choose like contradiction or entailment, it's not a fair in comparison. But I know for a fact that if you only choose either entailment or something, it would be, I think, 60 something %. So I mean, looking at it, like
well, even just basic, even without doing anything as simple as that, there are ways to analyze the hypotheses and do an NLP analysis of those and see there are certain patterns for neutral and entailment and negation just across each of those. And I'm curious whether these systems pick that up.
So if you look at here, like started from 48%.
Sure.
So way less than if you were only to choose like entailment or whatever, something else. So starts with way less than that. But I mean, you saw the state of the art is around 90%. Right. So it's more than that.
So you're talking about layer normalization, and I was just curious, what is a outlier? Can you help me understand like what an outlier is in this context and how that happens?
Yeah, I mean, let's say you don't have the layer normalization, so it's a neural network layer, and let's say it's a linear layer. So in this case, so the output could be any number. Let's say you start from the beginning and all the weights are randomly initialized. So the output of this feedforward network, because of these W's, these are random. So the output could be anything. Right. And I mean, with layer normalization, I mean, because it could be anything because of that random nature, if we don't add that layer normalization, what if like some of the outputs here gives us a very large number, and then that would, in the back propagation, when we are training, that would force the gradient to try to compensate for those outliers.
Okay, so you're just setting it between a min and max.
I mean, right now, the way, as I said, the way they do it, they just add layer normalization all over the place.
Okay, gotcha.
And the other experiment that I'm running is the whole transformer, but without residual and without layer normalization. I wish I had the results now, but again, I will add it.
What are the use cases where the transform likely to produce
better results? I mean, I would say the only case, I didn't try to make them like parallelize the whole system, but I would say that's the only case I can see based on my experiments. But I mean, there's another paper, I think it's a 2018 paper, and the way they try to handle NLI task is that, you know, we have hypothesis and premise, so they concatenate these two vectors, and then they feed the whole vector into a transformer model, and that's what gives us 89 point something% here. So that's the, but actually the other thing about that paper is that they did transfer learning. So first they trained the whole thing on like a bunch of other texts, and then they transferred, but they were able to get 89.9% here. So I would say, as I said in the beginning, so in this, when we look at the state of the art, people use all these different kinds of tricks, like transfer learning. In this case, it gave a very good high accuracy. But what if we do the same for RNN? Was that? So what would be interesting is to grab the same algorithm that they have, but don't do the transfer learning, and see what is the accuracy. That would be a more fair of a comparison.
I'm very curious to know if you found character embedding useful.
Character embedding usually, I mean, in this case, in my repo, still I don't have it, but I have used it before. Usually helps a little bit. Yeah, so it's not like if you add it, you would add like 10% or something.
Just trying to understand the multi-head attention. Is the idea that instead of having a fixed word by word grid, that you're actually doing letting the data decide the loci and doing kind of like a chunking to find where the attentions lie through the training?
So you know that when we have let's say when we use word embedding, like let's say 100-dimensional or 300-dimensional word embedding, each of these dimensions means something. We don't know what it is, but each of them has a special meaning. And what happens with this linear layer here, we try to map like a 300-dimensional vector into a 50-dimensional vector. And it's kind of the same as what happened in those dimension reduction system models like PCA. So we are trying to decrease the number of dimensions in order to understand what's going on, because 300 might be a lot, but like 300 divided by 475 might not be a lot. And because we are using different linear layers and they are started with random weights, they are hoping that each of them would give you like different perspectives. And what I had, I know this last slide doesn't make sense that much. I forgot to say that like each of these is like a different head. So you see that they're somehow different.
Yeah. So
it means that like each head, I don't know what they attended to, but we know that they attended to different things.
So, like going back to like your corpus, you maybe have some sentences that are, 30 words being compared against the hypothesis against the other sentence that's maybe 60 words, and
the max is 120 something.
Okay, max is 120, and then so you're doing like a dimension reduction to maybe like 5 or 6 or 10 attention.
No. The thing is that we do the dimension reduction on the embedding output. So if the embedding is 100 dimensional, it doesn't matter like how many tokens are in that sentence.
Okay.
We apply the transformer on that dimension.
So I'm guessing that by default, this is all English text. Have you seen any results in languages using these techniques?
Chinese? I mean, I've seen. I mean, you mean SNLI or using transformer?
The latter, transformer model. Are the results comparable in different languages?
I mean, with China, I've seen with Chinese. That's I think what they report in their paper. But I mean, always what's interesting, and that was my main purpose of creating this repo. I know it's still kind of in the beginning, but my main purpose is to coming up with like certain designs and comparing them so that we can have a fair comparison. Oh yeah, Marcy will do the next.
How long does it take practically to get an answer given the answer?
So I haven't measured that, but it's real time, I would say. I mean, if you go into my repo, there is an interactive mode that you can run it and just give your own sentences. It would give you the visualization and the answer. I mean, I haven't measured it because it was fast, but when I said like 10 minutes for each epoch of training, so basically, I mean, 80% training is the same as dev, except not 80%, I can't say a number, but I mean, if they train during training, each epoch takes 10 minutes, might be fair to say that during testing, it takes like 5 minutes. I don't know, I haven't measured that, but each epoch, if it takes 10 minutes, it was around 128 samples per batch and 4,000 batches. So you can do the math and see. So it was 4,200 batches, I believe, and each of them 10 minutes. So I've been running it since yesterday. Yeah.
Perhaps you could do a lot of sort of testing
Yeah, of course. And if you had any issues with the code, you can leave on the repo as well and the meetup page, I guess. Because as I said, there are a few things still exciting to see I haven't seen, but.
So I think we're out of time. So any other questions? Amir will be here afterwards to answer. But let's go ahead and give him a big round of applause. Thank you.
Thank you.